welcome you all in this presentation related with the subject fundamentals of surface engineering. And you know that we are talking about the thermal spray processes, which is one of the approach for developing a layer of the suitable material for improving the tribological performance. In the last presentation we have seen the basic principle of the thermal spray processes, and there is one more aspect related with the thermal spray processes, that the coatings which are formed will be produced one by one by development of these splats over the surface of the substrate, and these are the splats which are deposited. So, as per the particle velocity and their mass, the different splats one over other will be deposited. So, if we see each splat is one unit. So, each splat will have its own structure, while if we see the splats in the splats are in contact with each other at a particular surface. This one is called intersplat space or intersplat surface. So, the intersplat structure, this is another aspect. There can be pores, there can be inclusions, there can be other defects, there can be cracks, or there can be simple metallurgical bond. So, there are two aspects as far as the structure of the coating structures are concerned, or we can say thermal spread coating structure. There are two aspects. One is the intersplat structure and intra or within splat structure, and both needs to be seen separately. There in the intersplat structures there can be pores, inclusions, cracks, or simple metallurgical structure. While in case of the intrasplat structures, there will be primarily the metallurgical structure. Now, so these are the two aspects which need to be seen separately. Now, one more thing, since the mass of the substrate is very high, it is at low temperature. So, mass is high and the low temperature, and the temperature is low, while the particle mass is very small, it is very less, and the temperature is very high. So, because of this contrast, as soon as the particle impinges with the surface of the substrate, the heat is rapidly extracted by the substrate from this particle, and this in turn causes the rapid cooling of the splat, which is in the either in the semi solid state or the completely molten state, and this in turn causes the rapid solidification of the splats, and the rapid solidification of the splats can occur in the range of 10 to the power 5 to 10 to the power 8 degrees centigrade per second. So, these cooling rates are very high, and which in turn leads to the formation of the unstable phases, even amorphous structure which is not crystalline. So, these will tend to get stabilized as soon as the further rise in temperature of such kind of the coatings take place. And because of this, we do not find in the flame spread coatings or thermal spread coatings the typical microstructure is different from the stock material of same composition, which may be in form of like say the rod or the wire. So, this different microstructure is really very difficult to recognize that which constituent belongs to which type of the particle. Like say in the coating we have large number of the splats deposited like this. So, there can be nickel, there can be tungsten carbide, there can be chromium carbide, boron, silicon carbide, etc. So, it is very difficult in the flame spread coatings to identify which constituents belong to which particle. Because here we come across very high cooling rates, the semi molten or the complete molten state, and even just or in some of the cases even just thermal softening is taking place, and that is why we do not get that the common structures in the flame spread coatings, which are like maybe in form of planar structure or cellular structure or dendritic structure or equexed structure. So, these are the most commonly observed structures in the conventionally solidified material systems like in castings or the welding, and therefore, the identification and distinction of the various micro constituents in case of the flame spread coatings become difficult. There is another aspect related with the flame spread coating characteristics, that is the splats are deposited on the surface of the substrate like this, one layer by layer, one over other, this manner. So, if we take any section like this is one section, obviously in the so there will be the three different directions. One is the z direction, that is across the thickness direction, and length and width direction, which we can say as xy direction. So, the properties and composition of the coatings in xy direction, that is in a particular plane, they become by and large uniform, and variation in terms of the hardness and other properties is very limited. But if we see the variation across the thickness, like changing from or variation in properties, if we study from the interface to the top of the surface, then we find lot of variation in properties of flame of thermal spread coatings from coating substrate interface to the top of the coating. So, from the interface, that is this coating substrate interface is this, and this is the top of the coating, and there will be lot of variation in terms of the properties and composition. So, heterogeneity exists in the thickness direction, while in the xy direction or at a particular plane of the coating, the variation in the composition as well as properties is very limited. Now, we will see the one typical thermal spray process, that is called flame spray process. So, we have in this process a flame using the oxygen and acetylene, this mixture is burned, means combustion takes place and flame is achieved, which is mostly we use the neutral flame using the equal proportions of the acetylene and oxygen, which generates around the temperature of the 3000 degrees centigrade. So, for this purpose we have to feed oxygen, we have to feed acetylene in a particular chamber where these gases will be mixed. So, mixture of these gases will be obtained and then these will be burned. So, a flame is achieved and this flame will be coming out of the nozzle, and here we feed the feed stock in form of powder. So, feed stock is fed in form of powder in the flame. So, here the powder particles of the material which is to be applied onto the surface of the substrate, they will be entering into the flame which is at 3000 degrees centigrade and say moving at 100 to 200 meter per second speed. So, these will be now first of all these will be heated to high temperature so that they can either be brought to the molten state or semi molten state, and then these are when these particles are there in the flame, they will be accelerated towards the surface of the substrate. So, the acceleration will be increasing there the particle velocity, like say maximum up to 50 meter per second, and then these will be impinging with the surface of the substrate to develop the coatings. So, in this process, as we know, the temperature is around 3000 degrees centigrade, that is maximum temperature, while the particle temperature is limited to like 1500 to 2000 degrees centigrade, while the particle velocity is very limited like 10 to 50 meter per second. So, because of since in this case the particle velocity is limited, flame temperature is limited. So, the low temperature of the flame is favorable with regard to the reduced thermal damage of the feedstock material, but the limited particle velocity will be permitting the longer exposure of the feedstock material within the flame. So, as we have seen, a longer high temperature exposure of the feedstock material in the flame will be leading to the thermal damage of the feedstock material. This is one which may be in form of decomposition of the tungsten carbide particles or the chromium carbide particles, or their interaction with the oxygen, nitrogen and other gases which are present in the flame. So, this will be leading to the formation of inclusions. Further, the particle velocity and this why this is happening, why longer time of the exposure at a higher temperature, because of the limited particle velocity. So, limited particle velocity will also be leading to the reduced kinetic energy of the powder particles at the time of impingement, and which in turn will be leading to the reduced coating substrate bonding. So, bond strength is limited. So, there is a possibility of spalling or the delamination of the coating from the substrate and higher porosity. And we know that the flame which is obtained through the combustion of the acetylene and oxygen is a low energy density process. So, we need to in this process we supply lot of heat to the substrate gets there is a rise in temperature of the substrate as well, and rise in temperature of the substrate during the thermal spraying will be causing the residual stress as well as distortion related issues, one, and the second, it will be leading to the reduced cooling rate of the flame spread coatings. So, reduction in the cooling rate of the flame spread coatings will be leading to the coarsening of the grain structure. So this coarsening of the grain structure is an undesirable aspect. For the same material, we will be getting the reduced and the poorer mechanical properties. So as far as the flame spray process is concerned, there are few issues which are like higher porosity due to the limited particle velocity at the time of impingement, and reduced coating substrate bond strength, and third one is the very coarse grain structure of micro constituents in coatings. So these are the three issues, and it is required because even for the same feedstock material, flame spread coatings will be offering the poorer mechanical properties, and that is why it is required to improve the performance. For improving the performance of the flame spread coatings, it is required that some additional approaches are used for enhancing the performance of the flame spread coatings. As far as the properties of the flame spread coating is concerned, there can be 5 to 10% of the porosity, and the density is about 85 to 98% because of the porosity inclusions. This is one aspect, and the bonding is also very limited, like 20 to 40 MPa bond strength, which is achieved in this case. Apart from these issues, there are some commercial aspects which are associated with this process, like since the equipment used for flame spraying is very simple, so simple equipment, flame spray torch, and that is why it is of very low cost, and the simple equipment leads to the easy handling and use of equipment. And since the equipment is simple, it is easy to implement and apply and synchronize this process with the manufacturing system. So easy to implement with the manufacturing system of the process. The process offers a quite high deposition rate, which is a good side. We will be able to cover the larger surface area for surface modification, and the wastage of the feedstock material is limited. So this is another good side. There are few processes where particle velocity is very high, so after the impingement, particles tend to scatter here and there, and that will be increasing the wastage of the material. So here the wastage of the feedstock associated with this process, this flame spray process, is very limited. So these are the some of the good sides as far as the flame spray process is concerned. Now we will see some additional aspects related with this process. Whenever we develop any flame spread coating, in general we encounter some of the issues with the flame spread coatings, like since the coatings are developed by splat to splat bonding or bonding of the splats with the substrate, and this in turn leads to the limited the toughness of the coatings. With the some of the materials, there is a restriction on the thickness of the coatings which can be produced. In general, greater is the hardness of the material, smaller or thinner will be the coatings that can be developed. For example, the materials of like 200 HV hardness can be developed to the coatings can be developed of 1500 to 2000 micrometer easily, means 1 to 2 mm. Thickness coatings can be easily developed, but if the hardness is too high like 800 to 1000 HV, then this is limited to like say 200 to 300 micrometer. So, there are coating thickness restrictions. Harder is the material, lower will be the thickness which can be deposited, else the delamination and removal of the coatings will start. So, higher is the hardness, lower will be the thickness, and lower is the hardness, greater will be the thicknesses of the coatings which can be made by the thermal spray processes. Now, there are bond strength limitations as well, like as per the particle velocity. The coating bond strength thickness, like this is the coating and this is the substrate. So, the coatings do not bond very effectively with the substrate, because most of the time it is mechanical bonding due to mechanical bonding in form of mechanical interlocking, as well as little bit metallurgical bonding also takes place, but that is limited. That is why there are bond strength limitations, and as per the particle velocity, the bond strength may vary, like say from 20 to 100 MPa. It is always desired that the bond strength for most of the engineering applications is greater than 70 MPa as a minimum acceptable bond strength. But since the bond strength is influenced by the number of factors such as the surface roughness of the substrate, the cleanliness of the substrate, the particle velocity, the rise in temperature of the substrate, all those factors will be influencing the bond strength of the coatings. So, there are limitations associated with the bond strengths. For example, flame spread coatings offer very limited bond strength, and exposure of the substrate material to the flame, and this in turn, these factors in turn lowers the bond strength. And there are application difficulties, like the process has to be applied in the shop, and in all those difficult to access locations cannot be subjected to the coatings using the flame spray process. So, there are few application related difficulties as well as far as thermal spraying is concerned. Now, this is the schematic of the flame spray process, wherein we use oxygen and acetylene separately. Both are fed in the chamber where this flame is produced, and in the flame before getting outside the nozzle, we feed the spray powder or the feedstock material in form of powder through the hopper. So, this material, whenever it is fed, it will be heated in the flame, and then it will be accelerated towards the surface of the substrate. So, heating may be leading to the either complete melting or the semi molten state of these particles, and once these attain enough velocity as per the flame velocity as well as the standoff distance between the nozzle and the substrate surface, the particles will be impinging with the surface of the substrate, and they will be getting deposited in form of the splats. So, as I have said, since the flame spread coating process uses comparatively low energy density heat source, and the particle velocity which is achieved in case of the flame spraying is very limited, and which in turn leads to the issues related to the poor bonding, porosity, and coarse grain structure. So, to overcome these issues, some of the methods have been developed for improving the characteristics of flame spread coatings, and there are few categories of these methods, like methods for improving these characteristics of the flame spread coating. So, one is like densification of coatings. This may involve use of hot isostatic pressing or rolling or compaction during the flame spraying itself. The another method is the remelting of the flame spread coating. So, remelting is facilitated using the laser or the TIG arc. So, whenever the coating is remelted, the heat source is of the higher energy density. So, this in turn facilitates the controlled melting as well as the rapid cooling, which in turn refines the grain structure, while densification will be reducing the porosity and improving the bond strength. Similarly, there is another approach which is used for improving the properties is the controlled alloying. Now, as per the material system, we can use suitable alloying element, like for the aluminum alloys it may be titanium, for steels it may be aluminum or vanadium, and similarly the rare earth elements are also used in form of ceria or the lanthanum oxide La2O3. So, these are these elements will be helping us to refine the micro constituents present in the flame spread coatings for improving the performance. Since the flame spread coatings offers a coarse grain structure and the porosity, higher porosity ranging from like say 5 to 10%, and the bonding is poor. So, sometimes remelting helps in increasing the bonding as well as refining the grain structure. Densification helps in reducing the porosity as well as, and the controlled alloying helps in refining the grain structure. So, that there are different approaches for taking care of the various issues related to the flame spread coating, so that their performance can be enhanced. Now, I will summarize this presentation. In this presentation, basically I have talked about the way by which we should look into the microstructural aspects of the flame spread coatings and thermal spread coatings, because these structures are completely different from the conventional structures of the feedstock materials, as well as at the same time I have also talked about the various aspects related with the flame spread coatings and the kind of the quality which is achieved in the flame spread coatings. And we have also seen that there are some issues related with the flame spread coatings, like poor coating substrate bond strength, higher porosity, coarse grain structure. So, there are certain methods which can be used for improving the performance of the flame spread coatings. Probably I will elaborate these methods for improving the performance of the flame spread coatings in the subsequent presentations. Thank you for your attention.